Hello?
Yes, Professor.
Yes, we
Okay.
can.
Can you see the my
Can
slide?
see the slide.
Can, right?
Yes.
Okay, good. So we already passed 2/3 of chapter 1, the introduction to several variable function. So for the first 2 lecture, so we already study the xy plane, xyz space for 2 and 3 variable function, and more general in Rn. And then we study the limit of the function of several variables from the point of view of the distance. So pay attention, this is not modulus of the 2 points on the real line, a distance between 2 points on the plane or in the space. After that, we study continuity. So actually, the first 3 but more or less, we understand that it is the generalization of one variable to several variables. But the partial derivative is quite new, which is about the derivative of a function of several variables with respect to one variable, keeping other unchanged as constant. So this is important, and we will be using the partial derivative throughout this course, and you have to pay attention on that. And now we move to the last 2 sections of chapter 1. The first is chain rule. For one variable, we know that the chain rule is applied for differentiating of composite function, which means if we have a function y equal to fx, where x is a function g of t, then y actually is a function of variable t. And because of that, this is one variable of one variable of one variable. Then we can talk about y prime, or more precisely, we can talk about dy over dt as one variable. That's the reason we can write the normal d. Right? But to compute dy over dt of this composite function, first we take the derivative of y, or actually of f, with respect to x. So this is f prime with respect to x, and then multiply by x prime with respect to t. So you know quite well this situation. That one variable. What happens if we have a composition of function of several variables? So then it is more complicated in the sense that we have several versions depending on how many variables we can have. That the big difference between one variable and several variables. So first, we talk about case 1. What does it mean? Case 1 means we have a function of several variables in general. Here we talk about 2 variables, but each variable is a function of one variable only. So each function x and y are functions, but of one variable. In this case, what can we do? Now look at that. Suppose we have a function of two variables, w is fxy. Of course, everywhere we assume that function we are considering are differentiable. And each variable x and y is a function of one variable t. See, this is one variable t and differentiable. Then we have a function w, which is a function of one variable, So w now is fxtyt, but actually we can write a function of one variable t. Then we can differentiate w with respect to t with normal d. However, in comparison with this situation, when we have y is a function of only x, y is a function of one variable x. Here, we have y w, right, is a function of two variables. Then the derivative dy over dx we cannot do because we have two variables. So instead, we should consider the partial derivative. Instead, we should consider a partial derivative with respect to x, also with respect to y, because x, y have equal role. And after having partial derivative, we can take x prime of t and y prime of t, because each x and y are function differentiable with respect to t. In other words, we can write w prime at t, right? dy, dw over dt is partial derivative of f with respect to x multiplied by zx derivative with respect to t, plus the other variable, partial derivative of f with respect to y multiplied by derivative of z variable y with respect to t. That's the case one for two variables. Case one means the variable are function of one variable t. So for example, you are given a function w depending on x and y, where x and y are function e to power t and psi t, one variable. So you are asked to find dw in this set. We can write like that, right? Or we understand this one, or we write dw over dt. Apply the chain rule. Apply. So we have to find partial derivative of w with respect to x and y, and then derivative of x and y with respect to t. So dw over dx curly d, because this is partial derivative. So derivative of this with respect to x, we have 2x and y unchanged, 2x and y. This one, 3y, 4 unchanged, derivative of x is 1. So you have 3y4 multiplied by x prime of t, which is e to power t itself. That's the first one. And similarly, we have the second term. dw over dy here, x is unchanged. You have x squared. Here, 3x is unchanged. Y4 derivative is 4y cubic, which means that you have 12x cubic multiplied by dy over dt, which is cosine t. So at that point, more or less is okay for the first formula. But we can also represent this one star in terms of t, which means that everywhere we use variable t, then you substitute x and y in such a form to the formula. Then you have 2 stars. So is that. And next, you are asked to find the rate of change in W at t equal to 0. The rate of change talking about, we understand that this is derivative, dw over dt, and then at t equal to 0. So dw over dt, we can use either 1 star or 2 star. If we take 2 star, because everything you have is expressed in terms of t, then substitute t equal to 0. You have 0, 0, 1, 1, 0, 1. So you get 1. Right? But you can also use this one. But in this case, when you substitute t equal to 0, you should remember x, y at 0 also. So you have to compute x at 0, y at 0, then you get the answer, right? Evaluate x and y at 0, and you get exactly the same answer. So it is up to you. But more or less, in this example, we should remember the formula for derivative using the chain rule, and you should remember when we talk about the rate of change, it means that we are dealing with the derivative. Okay. Next example. The radius of the right circular cone is increasing, but at that point, we stop. What do we have? We have the right circular cone, which means that you have this. This is the cone, and the height is perpendicular at the center, and you have this right angle. So this is right circular cone. Radius here, if we write h is height, radius is r, then we are given the fact that radius is increasing at a rate of 1.8 centimeters per second. How to understand? We have radius increasing, which means that this base is bigger and bigger. In this case, of course, we have to push the vertex down. Then the height is decreasing, right? The radius is increasing, then height is decreasing. So we can have such a thing. That one, right? So these are this h. H is bigger, h small, smaller, h small, but r is bigger, r small. and rate of decreasing and increasing is about 1.8 and 2.5. And you are asked to find the rate. The rate is the volume of the cone changing when big R is 24 centimeters and the height is 14 centimeters. How about the rate? We do like that. Sum D with respect to some variable, the rate, the volume. So then we have to represent the volume in terms of R and H first. So we know this one. The volume is 1/3 pi R square, the area of the base, which is area of the disk, and multiplied by H. So this is a function of two variables H and R. This is the volume. And now how to represent, express the rate? The rate of change of radius. See, we talk about the timing. Now we see, we talk about a timing. Then here we understand that we should take with respect to t, the timing, right? Measured by second. So rate is 1.8 of radius increasing. Then it means that you have r prime with respect to t, or dr over dt is 1.8. But with 2.7 or 2.5, you have decreasing. Then the rate must be negative 2.5, because it is decreasing the rate. And you have h prime of t is negative 2.5. Everything is done. Now we should find the rate of the changing of the volume when radius is 24 and height is 14. So using the chain rule of two variables, a function v of r and h, then this is partial derivative of v with respect to r multiplied by r prime plus partial derivative of v with respect to h multiplied by h prime. This you have this one 1.8, this one negative 2.5, and derivative, partial derivative of v with respect to r with respect to h, you get here. So substitute the results. You want to know at r equal to 24 and h equal to 14. You get this one dv over dt is negative, which means that this volume is decreasing, right? That negative 76.8 by centimeter cubic per second. That we apply the chain rule of function of two variables to the real life problem, regardless what it is. We know we can and we must apply the chain rule for case one, because both r and h are function of one variable only, Okay, so how about a function of three variable? Again, case one, which means that each variable is a function of one variable. Okay, so in this case, we can surely understand what we have to do, because each variable x, y, z is independent and they have the equal role. That's why partial derivative must be taken with respect to each variable x, y, z, and then multiply by derivative. Okay, so or we can write like this. That one. So it's quite similar to case one for function of two variables, and very easy to understand why we have to do so, right? Example, you are given a function of three variables x, y, z, where x, y, and z are function of one variable, and you are asked to find the value of derivative of w at t equal to 0. Very easy, right? That applies the formula. You have, and you substitute each. You can find into the formula and try to, if you want, you can try to simplify this, or you can do that and then you substitute t equal to 0. It's easier because simplify here, we don't know how to simplify. But with t equal to 0, most of the things are gone, right? This t cubic gone. Logarithmic of 1 gone. Only y, which is cosine 0, is 1 remain. And x and z are 0. So then you substitute to this formula. The answer, derivative here is 0. That's the example 5. Okay. Now, what happens if each variable of a function of 2 or 3 at least, or several variables, is a function of several variables, not of one? So, for example, we talk about case 2, which means a function of two variables at the moment, x and y, and each x and y are function of two variables, which means x is a function g of s and t, y is a function h of s and t. Then w is fxy, which is f at gst and hst. This is w is a function of two variables s and t. So we look at this one and we understand in this case you can have the partial derivative because w now is of two variables. You cannot write dw over ds or dw over dt. No, this is wrong because this normally is for function of one variable. Instead, you have to write the partial derivative of W with respect to S and to T. Here, if with respect to S, you have a function W is a function of two variables. You can consider it is similar to one variable X, but depending on S. Forget T. However, you should not write dx over ds because X now is a function of two variables. Then derivative must be partial derivative instead of that. So you understand. Actually, it is with respect to S. But S and T are equal of the role, then you can also have W dw over dt exactly the same, only partial derivative of x and y now is with respect to t. That's all. So case 2 more complicated because you have so I take of two variables. You have see only one derivative because w is a function of one variable t. But for case 2, you have two in this case because f is a function or w is a function of two variables. Then you have two equations like this in theorem 6. Okay, so you should read carefully the question and recognize, determine what case you have to apply. Example 7 is simple because that only formula you have to do, right? So x, y, x is a function of st, y is also a function of st, and you are asked to find the partial derivative of w with respect to s and to t. Apply the formula here to s, here to t, and then you work on each partial derivative. Then you get the answer. No problem with that. Quite simple, right? Quite simple. That's example 7. Example 8. Now, what happened? Function of two variables. Yeah. But each variable a function of not two variables, are three variables. Then, of course, you understand that you should have dx over ds, dx over dt, dx over du. The same for y. dy over ds, dy over dt, dy over du. So you should have this partial derivative with respect to x and for x and y with respect to s, t, and u. But partial derivative of w, only two, the same. dw over dx and dw over dy. But each formula related to three partial derivative. So then you see you have first with respect to s if we want, because x and y both function of s, t, and u. Then w is a function of three variables. If we want to talk about variable inside s, t, and u, here only two variables if we want to talk about x and y. But then the chain rule apply to dw over ds, dw over dt, dw over du. And for each case, you have to take partial derivative of w with respect to x and to y and multiply by that derivative of that variable with respect to the same s, right? The same t, the same u. Then you get. So 3 partial derivative we need. Okay. How about the other case? Function of 3 variables, but each variable is a function of only 2 variables. That is, this is a function of only 2 variables s and t. If you want to consider the last variable, right? So then you have partial derivative with respect to s and with respect to t. And for each case, because x, y, z are of equal role, so you should have own partial derivative and then multiply by the derivative of x, y, z with respect to variable you want to differentiate, s or t, then you get the answer, right? So we change from the number of variable for the main function and the number for variable of the main function as a function of other variable. So here you have x, y, z, right? X, S, R, T, Y, S, R, T, Z, S, R, T, and you are asked to find du over ds at a particular point, r equal to 2, s equal to 1, t equal to 0. So we write a function u is of function x, y, and z here, right? And then we have to find the u over the s over the r over the t. But here you are asked to find over the s only one. You are not asked to find du over the r or du over the t. So that's why you should read carefully the question, right? You don't have to work on other partial derivative. Du over ds. Of course, u is of a function of x, y, z. You should have partial derivative with respect to x, y, z, and then multiply by that function with respect to s. X to s, y to s, z to s, and substitute the formula. You can compute, and at this particular point, you get the answer for each value here using this one. And then you get the answer is 192. This is not related complication of formula. Formula you should remember, but you should try to understand and to know how to do for each concrete case. Computation is not complicated, right? So, and now we don't talk about case 1 or case 2. We talk about general case. A function u is of n variable. So you have n variable. And each variable is a function of m variable, t1, t2, tm, x1, x2, xn, which means that you have xk depending on t1, t2, tm, k run from 2, 1 to n. That so big main function has n variable, but each variable is a function of m variable. In this case, of course, you can find all partial derivative, right? du over dt1, dt2, dtm. And you know now, you should take partial derivative of u with respect to each variable x1, x2, xn, and then multiply by x1, x2, xn prime with respect to t. Then you get the answer. That's very interesting, right? Very interesting. So pay attention. When n is the number of variable of a main function and m the number of variable of each main variable, so we can say main variable m and n, then it depends on what m and n are. You can have the different version of partial derivative using the chain rule. When n equal to 2, m equal to 1, we have case 1. N equal to 3, m equal to 1, we also have case 1. But when n or m or is 2 or 3, m, you have n equal to 2, for example, but m equal to 3, you have no more. This case, you have 3 variables for each main variable. Then you have to apply this situation. And remember this, you understand what to do. Only I remind you again that if you have a function of one variable, then you can write d over dt, for example. But if several variables, you should write d over dt in such a case, curly d, because this is partial derivative. Okay? So for example here, n equal to 4, m equal to 2. Then you have partial derivative of w with respect to 2 variables u and v. So 2 partial derivative, and you apply for 4 variable. Next, so it's done. It's done for the chain rule. But now look at implicit differentiation. You remember, right? When a function of one variable, when you can write y equal to fx, we understand that we express y in terms of x explicitly. But in case you cannot do that, you have x and y, some constant c, and y still a function of x. Then it means that you have implicit formula for function y. You cannot write y in terms of x. That's the reason we have implicit. For one variable, we know. For several variables, we can do the same. Suppose a function z is a function of variable x and y has the equation in such a form. How to find the derivative? So derivative of z as a function of two variables is partial derivative. And to do that, from this one, we apply the chain rule to the differentiation with respect to x. df over dx, dx over dy, df over dy, dy over dy, df over dz, dz over dy. Yes, this is the chain rule we just studied. But this one is 1. This is 0 because you have a function y derivative with respect to x, but x is independent. X and y are independent, right? Y is independent to x. So derivative with respect to x, no x there. We have 0. So that's the reason we have this situation and it's gone. Only that formula remain. This is df over dx. We can also, the same case, we find df over dy. Yeah, that is both derivative. You can see you have df over dz. What we want to do, right? Here, see? Here also, dz over dx, dz over dy we want to find. And that dz over dx, dz over dy. So, solving it, assume that it is non-zero. If it is 0, you cannot do anything. Then you can move this df over dx, df over dy to the right with the negative side and divided by df over dz. So you get this answer. That actually it is the chain rule applied to the explicit situation. We know that. We know that from one variable we have such a thing, right? So for example, you have a function z is a function of x and y, but not explicit formula. This is implicit formula. We cannot represent z in terms of x and y, cannot. But we know that it is a function of x and y. Then you are asked to find the partial derivative of z with respect to x and to y. Apply formula. You can think it is f, it is c. So this is the equation of the implicit function z of x and y. And we apply the formula dz over dx and dz over dy here. Dz over dx, dz over dy. Then you get this situation. Partial derivative of big F with respect to x over with respect to z. The same for negative for y, but both has negative side. Then you get the answer. Okay? Such the thing we have for chain rule. A chain rule and the implicit differentiation for several variables. So we stop at this point, the first half of lecture, and we take about 10 minutes or 20, even 50 minutes, 11, 25. We start to look at the most difficult part of chapter 1, which is approximation. Okay? So, short break. So we continue our lecture. The last part is approximation. And as I mentioned, this is quite difficult. You should pay attention, difficult even for one variable, right? So now we look at this approximation. Gradient vector, we already mentioned in the previous lecture. So this is a vector performing from the partial derivative of a function of several variables. So in the case, it's of two variables. F is two variables x and y. Then gradient vector is a vector with coordinate partial of f with respect to x and partial of f with respect to y. Similarly, we can have the gradient vector for a function of three variables. Again, you have partial derivative of f with respect to x, y, and z. And more general, right? You have a function of n variable and you can perform the gradient vector, right? But what does gradient vector have? Property. What property does it have? You should remember these properties, orthogonal properties, is very important. As I already explained, the word orthogonal, it is the same as perpendicular. Right? This is the same, which is vuông góc in Vietnamese, or Hán Việt là trực giao. But we say this one, okay? So now we look at these properties relative to function of 2 and 3 variables. And you remember, right? For 11 set, if we talk about 2 variables, we call this 11 curve. If we talk about 3 variable function, we call this 11 surface, because this is a curve in R2 and this surface in R3. But for n bigger than or equal to 4, we call 11 set, right? In Rn. So remember different name, okay? So, and in this case, we can use the tangent plane. Tangent plane, very important. Tangent plane to estimate the value of function of several variables and finding the estimating error. Cái sai số khi mà chúng ta xấp xỉ và chúng ta dùng cái xấp xỉ gọi là linear approximation, LX. So for one variable, remember we have LX. For several variables, we have more than one variable, LX and Y and X, Y and Z. So that's the idea. Okay, now the first properties, perpendicular. You see, I use also the word perpendicular. Gradient vector is perpendicular to the 11 curve. Talking about 11 curve, we understand that we talk about the 11 set for 2 variables, k, where k is a constant. So here, a function of 2 variables and on x, y satisfies this condition. We call the 11 curve, right? On x, y from R2 satisfying the condition f x y is the same constant k called the level curve, which means you have some curve on the R2, right? And suppose you have a point P0 on this curve, which means P0 which x0, y0 also satisfy this one, right? Because it belongs the same level curve. So at that point, you can have the tangent line, a tangent line. And what properties say about? At that point, if you look at the gradient vector f at this point, then you have these two gradient vector and tangent line at P0 are perpendicular. Yeah. Gradient vector, nabla. Remember, this is nabla. This one. Not this one. This is delta. Then gradient vector is orthogonal or perpendicular to the tangent of the level curve. This is tangent line. So that property, very interesting. Yeah, you see. That level curve as at the point, and then you have gradient vector, this gradient vector, this tangent line, they are perpendicular. This is orthogonality property. Okay? So, example, you are given a function of two variables, and you are asked to sketch the level curve of f which pass through this point, which means, so again, the level curve f x y equal to k. And what k is, we don't know. But from the given assumption, this level curve passing the point P0, 1, negative 1, which means F1 and negative 1 satisfy this condition K. And you can find this, which is negative 1. That is K equal to negative 1, right? And now you have to write down the equation of this level curve and sketch it. So you do fxy equal to k, which is negative 1, means that you have y is x squared minus 3x plus 1. It is a parabola. It is a parabola. Okay? So, and you have to find the gradient vector at that point. Then, gradient vector is performed by fx. Derivative of this with respect to x is 2x minus 3. And fy. Derivative of this with respect to y is negative 1. Then substitute x equal to 1, y equal to negative 1, you can get the gradient vector. Gradient vector is negative 1, negative 1. Where is that? In general, negative 1 here, negative 1 here. Then gradient vector like that. This is gradient vector. But you know that on the plane, many vectors are equal. If you have such vector, this vector, so all they are the same. But at that point, which is 1 and negative 1. X is 1, Y is negative 1. This is P0. Then you should have here. You should have this gradient vector. And we sketch the gradient vector, we do like that. And don't care what the level curve is. We know that this perpendicular to the gradient vector at the point P0 must be the tangent line to this parabola, right? Which is the level curve. So we should be sure that. Then you see this one, negative 1 and 1 here, this one, right? This P0, 1, negative 1, and you see you have this tangent line and that one. This is gradient vector. That and it's that. So understanding the situation and understanding the perpendicular or orthogonality properties of gradient vector with respect to the tangent line of the level curve, you can have such a picture very easily. Okay, so how about three variables? Exactly the same, but instead of level curve, now we have a level surface in R3. For the level surface in R3, you have at a point a tangent plane. So that's the reason we say gradient vector nabla f at P0 is orthogonal or perpendicular to the tangent of the level surface. And tangent here, we understand that tangent plane instead of that one, this tangent here, tangent line, right? Because it's for the curve, plane for the surface, right? So here you can see that one. Blue is surface. Point P, tangent normal. This the gradient vector, and that one is tangent plane. So you have perpendicular. Perpendicular means this gradient vector is perpendicular to every vector on this plane, right? So using this fact, we can come back to the very well-known formula you study in analytic geometry of high school, which is the tangent plane to the level surface. How to write? Usually you have the ball in the space and at point. So usually you have a ball in your high school, right? You have a ball here and you have a point on the surface. Then you are asked to write the tangent plane to the ball at this point. And of course, we can apply this situation because the level surface, of course, not the ball, this is more general, passing through P, and this has gradient vector as a normal vector, right? Trong tiếng Việt nó gọi là vector pháp tuyến. Đấy, tiếng Việt gọi là vector pháp tuyến là cái vector mà perform như thế này. Đó. Ví dụ cái phương trình ax plus by plus cz plus D equal to 0. A square, B square, C square not on 0. This is equation of the plane. And you have a normal vector, A, B, C. This is normal vector. If you have that one, then this is normal vector, right? So, by that reason, we can have the equation of the tangent plane, which is normal vector, the same as normal vector, right? The gradient multiplied by any vector on the plane, x minus x0, y minus y0, and z minus z0 on x, y, z in R3 satisfies this condition. Perform the tangent plane to the level surface at a point. To the level surface at a point. And this, of course, you can understand that this is a scalar product of two vectors. And you have this fx, fy, fz multiplied by x minus x0, y minus y0, z minus z0, because the gradient vector is fx, fy, fz, right? The product of two vectors, you have this situation. So this is exactly what you already studied in high school, right? So then we can have also normal line. What is normal line? Normal vector here. Normal line, it is a line containing the normal vector. Và người ta gọi là gì? Là đường thẳng pháp tuyến. Hình như là vậy, phải không? Đường thẳng pháp tuyến. Còn cái normal kia là vector pháp tuyến. So, and this line is perpendicular to any vector on the plane. So that's why we have this situation. For t is r. If t is 0, it means gone. You had this point. As the other point on this normal line depending on t. Each situation of a point corresponds to one t. So this is a normal line. In your high school, usually you have the following problem. Write down the so-called parametric equation, phương trình tham số. Yeah, đây chính là phương trình tham số of a line passing a point and have a normal vector or direction, some direction parallel to some vector or perpendicular to some vector, then you can have parametric equation in your high school. And this is exactly the same situation. But from the point of view, we look at the level surface. Okay? So, example. You are given an ellipsoid. Cái hình trong mặt phẳng người ta gọi là ellipse. Còn trong không gian là ellipsoid. Right? And this ellipsoid passing through the point -2, 1, and -3. Yes, you can have that. You can check easily. And you have to write down the tangent plane and normal at that point. Very easy. You know this from your high school. For analytic geometry, always easy to work on, right? Tangent plane, you have fx, y, z here, equal to 3. And the equation, we already talked about this one, right? So here the equation of the tangent plane, okay, at this point. So then you find normal vector, which is the gradient vector, by fx, fy, fz partial derivative which is here, and at a point P, -2, 1, -3, you have this normal vector. So you know equation, you know the normal vector, and then you get the equation. This is equation of the tangent plane, right? Using that one. Using that one. Yeah. When you find this, you can get, see, you can get the answer. You find this, you get the answer. This is equation of the tangent plane. A normal line again applies the situation passing a point P0 with the direction of the normal vector or gradient. Then you have parametric phương trình tham số for all r, right? When r equal to t equal to 0, you get exactly that point, which is -2, 1, -3, and that's all. That's very easy to work on this situation. The only thing is you should remember the definition of the normal vector and normal line, and how about the formula related to the tangent plane. Okay, so, and now here we talk about the tangent plane to the level surface, right? Level surface. But now you apply this to the graph, to the graph. Here, you know that when you have fxy, a function of two variables, then the equation z equal to fxy perform the graph, right? The graph of a function of two variables. So function of two variables is in R2, but graph is in R3. And then you can think about this graph, a graph of a function fxy is on xyz, for which z is fxy, right? This is graph. But this graph we can view as a level surface where we have this one. So this equal to fxy minus z equal to 0. So this is the formula fxyz equal to k equal to 0. This is the level surface, k equal to 0, and you get this, which means you can view the graph of a function of two variables as a level surface of a function of three variables, which is fxy minus z equal to 0. So, and then you apply the formula to that situation. Then you get the equation of the tangent plane to the graph in this form or that form. So it is particular case. Okay. Here, diagram. You have this a graph of a function fxy, or even you can view as a level surface, of fxy minus z, right? But at that point P, you can have the tangent plane, that, and it is done quite easily to find the equation of the tangent plane of the graph at a point. Remember, tangent plane of the graph, because the graph is already in R3. Okay. In summary, you have the equation of tangent plane to the graph of a function like this, one of the two forms. And of course, when you expanded it, right? Because this is the product of two vectors. We have this one, expanded it. You get this is AX, this is BX minus Z equal to D. So this is the equation of a plane. Surely you know quite well from the high school. Then this slide you should remember. Okay? So, and regardless this, we can have a remark for one variable. Then actually it become tangent line. Gọi là đường tiếp tuyến thôi, không phải là mặt phẳng tiếp tuyến mà đường thẳng tiếp tuyến. Then you have this one. See? Right. But for two variable, instead of derivative, you should use partial derivative. That's the idea. Very easy to generalize. If you forget, then from one variable, you can have immediately the formula for several variables. So, example. What example we have? Surface here. This point belong to this surface. X equal to 1, y equal to 1, and z equal to 3. So you have some surface, and you are asked to write down the equation of the tangent plane to this surface at a point. So what we do? Look at this as either the 11 set we talk about, or exactly what we already remember. Then we can use the formula, that formula, right? F at 1, 1, see? And then Fx, Fy, x minus x0, y minus 0, and you have z equal to that. Compute each component, you get the equation, which is 4x plus 2y minus 3 equal to z. Or if you want, you can write 4x plus 2y minus z minus 3 equal to 0. That this is the same, right? So no problem with the tangent plane to the surface. Apply what we talk about the 11th surface, right? Now, the last part, approximation. Because as we mentioned, we use the tangent plane for approximation. For one variable, remember, we already talked about, for one variable, when you have y equal to fx at a point x0, if we want to have the very near to x0 value of fx, x is very near to a. Okay, I write a here, not x0, to a, which means that this a value here, we can in general use the so-called the linear approximation Lx, which is here. This is Lx. That linear approximation we study in calculus 1, right? So when x is very near a, approximation of fx, we use this one. And this Lx is exactly the tangent line function, right? So here, see, you can, instead working on that complicated f, you find the linear function Lx, which is actually the equation of the tangent line, and you can approximate it. You consider fx is almost the same as LX. For all x very near, for all x very near to a point A. So now the question, how about two variable or three variable? Here we talk about two variable. Very near, we understand that the distance between x and A very small. So that's the reason. Small means that distance from a point to a fixed point, very small, or this point very close. We want to find the value of x, fxy, where xy very close to a point P 0 AB to this point, and where x and y very near, very close to that. Can we find the value of x and y? Yes, we can use this approximation linear to find it. Yeah. First, equation of the tangent plane we already talked about, and that part is exactly LXY. This generalization of LX we talk about when we have one variable. So with this LXY, we can have not only the equation of the tangent plane, but also the approximation. Here, the answer. For any point on R2, XY, which is close enough to a fixed point AB, we can use LXY to approximate FXY. So this is almost the same, which means FXY is almost the same as that one. Or we write this with some error, với một cái số sai số nhất định. Và chúng ta có thể lấy được, đấy chính là cái xấp xỉ đấy, giống hệt như là one variable function. So the idea here is, instead of finding the surface, so you see, you have AB here, AB, that point P, and you have a surface, blue surface, and you can find value at very near this point by using the orange, that orange. This is the tangent, right? Tangent plane. This is the idea. Because they are almost the same, only different, very small different, estimating error, sai số của cái sự xấp xỉ. Chúng ta có, for example, here, real life, more practical for you, for tutorial, for midterm, for final exam of calculus 2. Exactly for similar to the case of one variable. You are asked to use linear approximation, LXY, to approximate the value. How to understand this one? So this should be some fxy at some point x0, y0, or at some point A and B. Okay, so we write A and B. So then what is fxy and what is AB? Here, we look at this fxy, and 195 almost the same as 2.0, right? So this one almost the same, 8, 2, right? So that's the reason we can think about A equal to 2, B equal to 8, and we look at a point. This is fixed point, and this approximation f xy, where xy is 1.95, 8.1, very close to 2 and 8. Then we have the formula we already have. fxy here, almost the same as lxy. And substitute x equal to 1.95, y equal to 8.1. You get this value almost the same as that one, which is computed it, because here you have partial derivative, right? You computed it and you substitute this x and y, you get the answer is 9.99. So this is almost the same as exact value with a small error of estimation. Okay, such the things we should pay attention. And from that, we have differentiation. Differentiation, remember, for one variable, you have differentiation df, which is f prime dx, right? If f is fx, you have that differentiation. You also have delta f, which is increment. Mà trong tiếng Việt chúng ta học cái thời xưa, khi mấy chục năm trước tôi học, người ta gọi là gia số hay là số gia đấy, số gia. Khi mà làm tìm đạo hàm này, cho x một số gia delta x thì chúng ta sẽ có một cái số gia của delta y. Thế rồi từ đấy các em tính lim đến ra được đạo hàm thì chính xác chính là cái increment. So for one variable, so for two variable, we can have the same. If we have delta x and delta y, increment of x and y from a b to each direction, delta x and delta y, you can have delta f, which is new value substitute the old value. Đấy chính là số gia. This is increment. This is increment of two variables, right? So then, because we can have linear approximation for one variable, and we already talked about linear approximation for two variables, then we know that we can apply the idea. The idea for approximation in one variable is this differential and increment we can consider the same. That is more difficult to find. Differential is easier when we compute the derivative. This idea we can apply to several variables to have function linear and delta f. This is increment of f when you have increment of x and y. So because of that, you have delta, then you have d, then we get the definition. Total differential or simple differential. Why we have a total? For one variable, we have df, which is f prime and then dx, because dx the same as delta x. But for several variables, we cannot say only differential. Differential with respect to what? Partial derivative. Then we need the so-called total differential, because it depends on both partial derivative, which is df. Total differential is partial derivative, see, f prime delta x with respect to x plus f prime with respect to y and delta y. So that's why we have the so-called differential total. And that idea, that definition will be used in one of the topic of chapter 3 and 4, which is the exact differential equation. That We will mention it later when we move to the chapter 3 and chapter 4, the second part. So this is total differentiation. And we have approximation. As I mentioned, delta F is more difficult to find than DF. DF here, easy to work on that, right? In where delta F, that terrible. Yeah, so complicated, this delta F. That's why we use DF, which is easier. The same situation, we can look at this where delta X and dx is the same, delta y and dy is the same, and then you get exactly the increment like this. Here, delta z or delta z. But approximation, almost delta z here in the surface, approximation in the plane. That's why we have such a thing. Let's see where I write the word easier to find. Here, delta F is approximately equal, right, to DF, but DF is much easier to calculate. That's why we change to DF. And that example, you have a function of two variables, you change x from 2 to 205, y from 3 to 296, and you are asked to compute DF and compare with delta F, which whether they are almost the same or not in this situation. So with A equal to 2, B equal to 3, you have delta X and delta Y. Delta Y is negative because from 3 decreased to 2.96. So you have A and B, you have delta X and delta Y. Then you can compute Fx and Fy as the partial derivative, and you get the formula df. Df is partial derivative at each point A equal to 2 and B equal to 3, and the result you have 0.65. But delta F, you have to use this formula. You see, quite complicated. And the result is 6449, 0.6449. And here is this one, df is 0.65. Not so big difference, right? And that's the reason you can see, yeah, it's really true that we can approximate delta F by df because it is easier to find. Okay? How about 3 variables or more? Exactly the same. You have linear approximation. You have total differentiation. So total differentiation is gradient vector multiplied by that. And for n variable, you have the same. N variable for linear approximation and total differentiation for n variable. And this is done for chapter 1. Okay, so today we have chain rule, different chain rule version depending on n and m. N is number of variable of a function. M is number of variable of each main variable. And have I provided several of the example. And after that, we use this idea to have the approximation, linear approximation from point of view of one variable. This is we use the tangent line. For several variables, we use the tangent plane, especially for the graph of the function fx, y of 2 variables, because graph in this case in R3. So revise this when and do when your the tutorial. And as I mentioned, if you have any problem with your tutor, first, you can discuss with your classmate about that. Second, you can ask the tutor directly. And third, if both don't work well or you are not satisfied with these two methods or two discussion with your classmate or with your tutor, you can write email to me and we find a way to classify, to clarify. Okay, that's all for today. Any question? No?
No.
Okay, then see you next week. See you next week. Bye-bye.
See you next week,
Bye, teacher.
Professor. Goodbye, Professor.
Bye-bye.
Bye, Professor.
Professor.